As the first thing, we'd like to solve one of the problems here. It's in chimera learning, and it's focusing to a gamma carbonic anhydrase structure. Exercise GCA is the one. And there are spoilers in part 2, which you may have seen when this was visible previously, but perhaps not. But anyway, we'll start from the beginning of this one. So please get this, and you might want to open Chimera and retrieve the model which is hinted at in the PDF. So here we go. 1QRE is the thing you want, and it's something, once you've opened the file, it's something that looks like a bar of Toblerone plus 1 alpha helix on the side. So lovely triangles. You just love to go snapping from one end and start chewing, but unfortunately they are just in a nanometer scale, so they wouldn't be much to give you a sweet taste on your mouth, even if they were chocolate. So the task here is to identify the active site residues of this enzyme, and the problem here is that they seem to be kind of in strange places, and also when you look at a UniProt entry and a PDB entry, the numbering doesn't necessarily match. So for instance, now that we look at the sequence, the first visible residue here is number 4. But looking more closely at the sequence, there's actually minus 33, and that is definitely something which is not as that numbering in UniProt. They always start from 1, and so this is probably with a signal peptide not counted in the protein numbering, and this is by the mature protein numbering, which will be starting from 1, and even there the first 3 residues are not visible, so this starts from threonine 4. So the red rectangle here indicates that it's invisible part, not in the structure, even if it has been in the actual protein sequence. And let's see how this is in the PDB sequence tab. So I have opened 1QRE. It starts with the structure summary. We can see that it's a decent quality model with most of the sliders in the blue region, and the sequence tab here gives us some ideas of where the sequence is. So we have unmodeled parts which are here up to 37 in PDB numbering. So we can see that PDB numbering indeed starts from 1 and not minus 33. So we have to figure out what to add or subtract into the sequence numbers to convert one to the other. And I'm opening the PDB link in a new tab. Actually, this is a link to the PDB represented in, sorry, the UniProt sequence presented in PDB, and let's see if we have a PDB link here. Sorry, a UniProt link. No, but no worries. We can just copy this and open our UniProt page. This is also something you need to do on your computer if you want to follow with the exercise as I intend you to. So let's see if we can find something about the active site here. So PTM processing, indeed there is a signal peptide here as and the signal peptide cleavage is one post-translational modification you can find, and this also happens for archaea. This is an archaebacterial sequence, metanosarcina. And let's see if the family/domains has something that helps us in the active site. Not right there. But what we need is the feature table here. So going to the feature viewer. Let's see what we have. Here we have structural features, which are probably beta sheets. This is an interesting model in that it is almost entirely of beta sheets. There's a long alpha helix in the end and a shorter one, but these triangular things are short, about 6 to 7 amino acid long beta strands, which are going round and round, so that each side of this triangle, if we look at the model in Chimera, each side here is like a parallel beta sheet with how many strands? 1, 2, 3, 4, 5, 6, 7 here. And then some of the strands are marked as continuous so that they are bending from one side to the other. But still they are parallel all the time, so it is just winding around. There's a little bit of an insertion here which is interfering the regular sequence of these beta strands, but most of this is really nice and regular, and this is very unusual for a protein structure that it is so geometrical. But I was looking for the active site residues, and let's see if we find them. They are not in the feature viewer. We have multiple models for the same PDB entry, but we are working with this one because it has the best resolution, 1.46. Okay, so let's go for the entry and see where we have the active site information. I think I missed it in the feature viewer. They had a link to sites there.
Yeah, there's like 2 active sites, one at the position of 96 and the other is I can't find 118.
Domains and sites, they are here indeed. Yeah, so we have yeah, I think it's these. Let's see if we can. Binding site. The active site is marked as 2 residues, which are these pink things. Yeah, 96 and 118. Yeah, you mentioned them, and then we have additionally. Let's see what we have here. Metal binding site 93 to 95. 109 to 110 and 115 and still some more. So the actual metal binding is between histidines, and we can see some of them already here in the model. So the metal is here, it's cobalt, even if zinc is the actual ligand. This has been crystallized with cobalt. And whenever we have some heteroatom groups, the way Chimera handles them is that it's locating all the amino acid side chains which are nearby, and they are visualized as the side chain sticks, and these are now histidine 81 and histidine 122. And we should figure out how to convert between between the numbers here and the numbers in the PDB sequence. So we should find 3 histidines out of these numbers, and then we can see how they relate to these ones here. And maybe we have a binding site even in PDB itself. Let's see how we have the annotations. This is just domain annotation and gene and protein functions. Maybe here in the sequence we would have hints of the active site residues. Okay, here we have binding site, which is marked as, come on, mouse over, please. Okay, this is a binding site for cadmium in addition to cobalt and zinc, but there's no cadmium in the model. This might be a mistake. But anyway, the metal binding site is indeed here. It's these purple or blue things. Now the numbers are actually at the top right corner. So this here is position 41, and this is position 93, and this is position 103. And I wonder how this relates to again, this seems to be UniProt numbering. No, sorry, my bad. This is actually, that was a different entry. Oh my. Right, that was the cadmium carbonic anhydrase. So let's go back here, and we have the binding site here, and these are positions. Now we have the 2 numberings. If you look at the top right, so this is positions 98, 99 by UniProt, and the author numbering is 64 to 65. And sorry, that was for the cis peptide. For the binding site for cobalt, so we have here 115, author 81, and here 151, author 117. You might want to write them down in a computer notepad or even on paper if you happen to have pen and paper at your desk. So 122, 117, and 81 by author numbering. Let's see if any of these are already here. Okay, 81 and 122, but where's 117? So I'd want you to solve this problem for a while on your own. Let's see what other parts are in the task list now that we have gotten started in solving the difference between numbering of the authors and UniProt. And you might also then check the 2 binding or catalytic residues that were mentioned in UniProt. You can figure out the difference between the numbers from these histidines. Okay, so here we have the active site and metal binding. I already copied it into this document. So you need to do the math and subtract a little bit from these numbers to come to the author numbers. Is it 33, 32? Anyway, you'll see the difference. Let's go here. So here we have 115 to 81, so there's a difference of 34 in fact, and it should stay the same. Indeed, 34 difference. And so we don't have the catalytic residues here in the way they were presented in UniProt. So these two active site residues, which are 96 and 118, you should figure out their numbers and visualize them. Likewise, the third histidine in metal binding. So I'll leave you with that for let's say 9 minutes, and I'll be back at 5:30, and we'll go on at looking at your solutions and then starting with the second part of the mystery. Okay, the glutamines in the active site are 62 and 84 when you do the subtraction of 34, and we can select them, and then once they are selected we use actions, atom bonds, and show, so they will become visible, and glutamic acid, and you can see that they are in a logical chain starting from the metal binding, so they form a kind of a proton shuttle there in the similar way as in the beta Ca we have the aspartic acid and arginine system working in a similar fashion, and let's see the third histidine, and then I had the command name cell active site, and this is creating an easy to remember name for this selection, so that we don't have to remember the numbers. And when we look at the backside using the lightning link here, so we can see that we have the selection called act site. And so now even if we lose the selection, so even if we lose the selection, we can go back to the active site selection, and clicking on it, they are selected again. And then we can create another one, which is selecting the residues. Need to check again. That was 81, 117, 122. Too many columns there. And so when you did this, did you realize that there's actually something that's selected so far away? And again, we can do the same thing, go for showing the side chains, showing the atoms, and then we can call this like call it as, say, bind site for short. So this allows us to to recall them, but indeed it doesn't seem to be binding the cobalt at all, and still it's marked as the binding residue. If you look at the PDB page, I'm not sure if you spent any time there now that I already gave you a hint of the numbering. So we have the, going to the summary, we have the biological assembly, which seems to contain 3 of these, and the asymmetric unit which we see in the crystal structure is only a monomeric form, and there is just a single biological assembly. And there was a hint in the end of your exercise document, and it was referring to the unit cell tool in Chimera. And if we go there, we find it in tools, higher order structure and unit cell. Let's see if it would have been available just typing help unit cell. No. Okay, so when we have a near perfect symmetry in a crystal structure, the unit cell might be formed with just a single copy of the atom, or it could be that there are multiple copies in the unit cell, but again, if they are so similar that they can be just modeled as identical structures, so they are not shown in the PDB, but instead the PDB file only gives the instructions for creating the symmetrical copies from the one which is displayed. And in these higher order structure tools, we have the unit cell tool, which will help us to make those copies. So we have the space group. I'm sorry, I'm not a crystallographer, so I can't help you with that. There's a cubical unit cell, which we can see from 90-degree angles, and the same dimensions for all sides of the cube. And crystal symmetry is 12, space group symmetry is 12, so probably we need to expect that we get 12 copies. And making the copies, there are many of them. And I'm wondering if there is something strange. There is something strange going on. These copies are moving relative to each other, so I need to go back to the unit cell tool and remove the copies. What happened here? My structure analysis, higher order structures. Come on. No, higher order structure and unit cell. So delete copies. Okay, we are back to just this one. Let's go back to making the copies again. And now we can see that our original one is here, one that's labeled number 0, and its partners in the trimeric biological assembly are number 10 and number 7. So to make things easier, we might want to delete models number 1 to 6, right? Number 7, number 10. And then delete 8 to 9. And finally 11. And again, oh no, oh no. I think what we have here is tiling has been forgotten and it's been left on since our previous exercises. Okay, I have untiled and now this works as expected. And I think the mystery regarding the third histidine is becoming solved. Can you see what's happening here? It's participating in a neighboring binding site, the one that is with subunit number 10 or model number 10 in the 12 copies. It seems that one of the glutamic acids is there for that one, even if it wasn't for ours. But now that we have made those selections, let's see what happens if we select the binding site. No, it doesn't do anymore. The reason being that it selected the atoms that were present in the models, even if our syntax of selecting those residues are not change specific. Now we have to do it again. And we can redefine the binding site. And yes, we want to show the atoms. And now our original binding site with those two histidines and the cobalt atom, the geometry is becoming more obvious so that we indeed have the third amino acid which is participating in binding. My apologies for not realizing that tiling is a function which remains there even when you close the session that had the tiled models. That was the 8CA version we were creating yesterday. Okay, so I'd better make the file visible to you. So going here and going for showing. So now when you update your Moodle page, you should get the part 2 and you can follow the rest of the story from there. So if you had gone as far as opening the original article describing this gamma CA, it would have told you that it works as a trimeric protein which binds 3 metal atoms and has 3 active sites. But each of the active sites is in the interface of 2 of these subunits in the trimer. So this is kind of cool. The creation of the site which is quite hidden here inside the protein. Let's see how a surface would look like here. So let's create a surface to everything. If we do the surface from menus, it will only use the selected atoms. We would get a partial surface. But now that we are giving the command, it's using all the atoms in the model. And we have the binding site selected. We might want to give it a different color. So let's say that we have color cyan, or light sea green, that would work. So there we have the histidines which bind the cobalts. And we can also do color orange for the cobalt residues.
I'm sorry, what was the command for deleting the unnecessary models? Because I have 12 models right now.
It's delete, and if we refer to the models with hash and numbers, you can use 1-6, and then I think you could even do 8, 9, 11 in one go, but I did that with 3 different commands.
Okay.
But they are gone, so they don't do anything in my view here.
Thanks.
And now maybe we need a little bit of surface transparency. Let's see if transparency 40 would be good. If you don't specify anything else, so surfaces are affected. If we want to change the sphere presentation of the atoms as seen in yesterday's partly unsuccessful demo, so you need to specify (A) after the percentage. That was my problem when it didn't work. So it wasn't that atom spec was needed, but I needed to have the right target. And this is really cool. We have these ends of the trimer going along to each other like you, as if you were braiding hair, so they are just spun around each other. There we have one active site. We have the histidines shown as blue, and then the cobalt is the orange thing, and here's a second one, and we should have the one which is between the brown and green. And between green and yellow, it's here. So we can see all of the binding sites here, and we can kind of imagine that the substrate bicarbonate, in this case HO3 minus, so it's just swimming in and gets converted, and the surface is almost reaching the cobalt atom here. And if we go for removing the surface, that was only removing the surface for the histidines because they were selected, but maybe it's not that bad. We can go for actions, atom bonds, and show as spheres. So now you can see that the histidines are really snugly there. And now that they are atoms, we can touch them. Here's 117, 81, and there's the 122 of the neighboring chain. So, and in each case, this is nitrogen epsilon 2, nitrogen epsilon 2, and also, this is ND1. It should be the epsilon. This might be a problem in the naming. Well, never mind. Anyway, it's nitrogens in the ring structure of histidine, which contains 2 nitrogens. And this is kind of intriguing, so that you can like be an intruder into the enzymatic activity and just peek it from the very narrow entry you have between the walls of the active site formed by the dimer. Let's go for a higher transparency. So if we do 60, it still doesn't work, because when we have transparent meeting transparent, which is like the other side of this subunit, so it will not let us see through. Only a single transparent layer will be showing something. So I wonder what is the transparency of our ribbon. We don't even see the ribbon there. So transparency 0 for ribbon. Okay, that was the reason. We had a semi-transparent ribbon, and that's why it wasn't really showing inside the transparent surfaces. Now we can go back to more reasonable levels of transparency. Okay, let's do 30% transparency on the surface and 0% transparency on the ribbon. Okay, 60% transparency on the surface. Now we have a kind of a semi-transparency that allows us to see the protein backbone, and also we probably want to have no transparency for the atoms. Yes, so now we can see the histidines where they are, and we can see the tiny little ball of cobalt. It should be bigger, in my opinion. These atomic and ionic radius values are not totally standardized, and I've seen them presented bigger than Chimera gives. But again, that's something we could change. So let's say we select the cobalt residues. We go to the selection inspector, and we can see that the radius is 0.56 angstroms. And if we think that we know better and think that it's 0.86 actually, so we can just change that. Okay, it happened. It is already bigger. So it's way bigger than the waters that are next to it, and we can see it a little bit clearer. For the sake of making a better looking model, we might exaggerate some features like the size of the metal atom to make it more visible. Let's see if we covered everything in the task. So we have rebuilt the symmetrical copies. And by the way, we didn't do the unit cell borders. That's something we can also do with the unit cell tool. So we have the unit cell outline, which is so when I clicked on the outline, I did get the unit cell there, and out of the 4 trimers we had there, so this one is occupying like one corner. And if you want to get rid of the outline, so just click on the outline button again. But that's helpful if you're kind of wondering where your coordinate starting point is. It is defined by the unit cell as it's coming from the crystallization, and how the molecules are oriented within the unit cell, that is different for each protein, and maybe it could be even different for the same protein when it's crystallized in slightly different conditions. Okay, let's go back to the instructions. Okay, and we got the extra copies removed by identifying that the ones we needed were 0, 4, and 10. And in this example, the model 0 would be here. It is recognizable by the tan color by default when you start opening new models in Chimera. So the first one is given in light brown or tan, and the second one is in cyan, and so on. So it's the same cycle of colors that's coming in. And in this exercise, we don't have much else there. This is a display which I think is no longer in PDB. And by the way, let me go for recording for now. Okay, we can pause the record. Okay, the second example for today is a morph between two forms of recoverin. This is a protein we find in the eye in the photoreceptor cells, and the name implies that it's functioning in the recovery from the light signal, so that the receptor cell is becoming able to get another signal of light, and it's a rhodopsin kinase. It phosphorylates rhodopsin, which is the main receptor part and main receptor there, and this phosphorylation, dephosphorylation is related to desensitization and recovery of that. And this is small enough so that we have NMR structures possible. NMR only works for molecules that are between 20 and 30 kilodaltons easily, and maybe in a stretch it could go to even 40. And if we look at this from the morphing start, so we'll see that this is from 1 into, there's the other end, into 188, so less than 200, and probably not much over 20 kilodaltons in molecular weight. 110 more or less is the average molecular weight of an amino acid in a protein. Okay, and this is an NMR ensemble structure. When you start solving your structure, what you get from the measurement is restraints between specific atoms, and sometimes maybe angles between some atoms, but the restraint information is most important to figure out the model, and the restraints, depending on the order in which you apply them, can be solved in many different ways, resulting to slightly different structures, and some parts of the model might be more clearly defined so that there are so many restraints that they always come up equal, but this is what an ensemble of 20-something models would look like. And this is the form that has the calcium missing, and in the calcium free form we have a form in which the fatty acid which is in the in the N-terminus of this protein is hidden in the protein core. But when calcium binds, so the fatty acid becomes free to interact with the cell membrane. It will go into the membrane and anchor the protein into that. And there will be quite drastic conformational changes. So here we have the calcium binding form, in which you can see that the fatty acid is indeed freed from the protein core. Here it's in a clearly defined conformation, and when it's free, it can be basically anywhere. And these green guys here are the calcium atoms. And what I've done for the Chimera session file is to delete most of these models. So there's 22 in the blue model and 24 submodels in the tan model. And I chose one of them which has the fatty acid very far away, and I forget what was my criterion for choosing the fourth one of the other. And with the OR operator, I'm selecting all the atoms from the two submodels that were selected, and with the command cell invert, I'm changing the selection into its complement, so everything but these two models are selected. And then deleting the selection, del cell is getting rid of all those. So starting from here, after these 4 commands, or actually 3 commands and 3 comments. So after the 3 commands have been executed, we have just single chain from each model. And now what we want to do is try to morph between the calcium-free and calcium-bound form. So we need to do superimposition first, so we would do a matchmaker, and after that going to the structure comparison tools and morph conformation, we should get them. So let's see. Matchmaker, I have a quick link here, selecting, let's say, the blue one as the reference structure and tan one to move. And okay. Now this is not a totally clean superimposition, as you may see. So it is the bottom part which is really well superimposed, but the conformation at the top is quite different because the calcium binding is doing such a lot to change the conformation. So if we look at the tan model, let's go for just unshow the blue one. So you can see that the calcium is binding a loop very tightly together and binding this adjacent alpha helix also very tightly together. And the same thing here, the calcium is in a loop which is held together by the amino acids binding to the calcium, whereas in the other one, where the calcium is missing, so these loops can hang out in quite free form. So this is the thing that is pulled together. And where's the other calcium binding site? So here's one, and here you can see that the difference is not that great. So you have a slight movement of this, but then there is a movement of this alpha helix, and that is something that is creating havoc in the orientation between the domains. So the next alpha helix is moved a lot from its original position, and then here in the calcium binding site it's really messy. But let's see how to morph between these two now that we have the superimposition created. What happens in the morphing is that it's creating a new model, which is actually a series of submodels or a trajectory that is taking you from the first state to a second state. And tools, structure comparison, morph, it's here. So first we have to add a conformation, and we got the menu kind of hidden away here at the bottom left corner. So we start from, let's say, the blue one. Oh, we start from blue one. And now clicking on add, it will should pick this conformation into the list. Come on. Okay, I double clicked, so I got it there. And then I will add a second conformation here, which is the tan guy, and then I'll come back to the original one. And let's see, we have 20 interpolation step, which might be okay, which is between each of the morphing steps here. And now clicking create should start to do it's there. It says computing interpolation trajectory frame 16 generated, going on, and there we go. We have 41 frames there, so it's like 20 frames going from start to the beginning. So it's the beginning 20 frames to the turning point, and then another 20 frames to the ending point. And now we have these play buttons. Let's see what happens when we start playing. And there's loop selected, so, and there's a slider for the speed. So it's kind of fast, so let's slow it down a little bit. And now, as I said, the originals are still there, and the morphing trajectory is a third object. So we might want to go to the model panel and hide the models 0 and 1. I'm unclicking the show, and there we go. This is clearly not a realistic way of doing this. You can see that the fatty acid is going through the protein, but it's kind of giving an idea of how much the secondary structures of the top domain need to move to tuck the fatty acid into the structure. So there's a rotation which is it almost 90 degrees. It's a lot anyway. And that is only triggered by 2 calcium atoms tightening those 2 loops, so that the protein, the top domain is forced into a quite different conformation. And you can see that the bottom is staying pretty much the same. There is a slight movement of this alpha helix, as we saw. The calcium binding calcium binding site is here, and the loop is loosening and tightening when we are doing the interpolation between the calcium free state, which is here, and the calcium bound state, which is here. But let's have a look at the animation I created previously. So if you need to get back the controls here, so there's a command that helps you do it, but you can also find it. So just stopping here, you can find it using the windows or the active windows here. So let's have a look at the morphing movie I had. So morphing trajectory MP4. 2 seconds only, that it can't be that. Oh, that was a different morph. That was a different morph. Okay, I have another Python file which is the morphing end. Let's have a look. That one has a few more. That one has a few more settings created there. So I've created surfaces and other stuff. So I'll close the session here and then I'll go for opening the morphing end. And when you open a Python session, or a Chimera session several times, so the first time you save it, it has only the py, but then when you reopen it, it's also creating the pyc, which is pretty much identical when you reopen it. I don't know what is the difference there and why the other one is created. But reopening Chimera and opening the morphing end here. Well, it's loading, so we might have a look at the morphing study document. Okay, so the thing to remember when you set up your morph is that you have to define the starting and ending conformation there. And if you want to loop the video, so it's a good idea that you also create a return morph to the original conformation. Then it becomes easy to show without a twitch to do a repeated loop there. Okay, what do we have in the session? We don't need unit cell, we don't need model inspector. Let's see what we have in model panel. We have surfaces, we have the morph. We don't have the morph. My apologies, this is not the morph we were looking for. So let's try another morphing end, which is this one, morphing 2. Open with Chimera. Now we do have the morph. We have the playback things here, and let's go for play. And now with the spheres, I didn't want to do surfaces because rendering surfaces would be too slow for showing this movie without recording it with the recording time of several minutes. But here we can see that this is indeed pretty well buried within the protein now that we have a different coloring for it. So going for pause when it's in the calcium-free conformation there. Maybe going for one step further back. So while this is running, we can do any kind of resizing and moving, and the same morph is just going on and on. So you can certainly see it's here, and if you do coloring by hydrophobicity, it shouldn't be a surprise that a fatty acid is hidden within a hydrophobic environment. And if I take the playback tool back out, so now we can see really that this is a complete transformation for the top domain. There is a little bit of sidechain movement here, so we have some loops turning at the bottom domain as well due to the calcium binding, which is about here. We can see that we have a methionine here with the sulfur atom, and I'm trying to see if we have any disulfide bonds here, which would be two yellow sulfur atoms which are connected. No, that's another methionine top there. But this gives you an idea of how much a single protein can change just by the simple fact of calcium binding. So I think here we can see a lot of turning. This guy is going, it's more than 90 degrees. So now it's more or less at the vertical position, and here it's going below the midline, this aspartic acid. I would say that this is probably one of the coolest molecular visualizations I've made, and certainly helps you understanding the changes between the calcium-free and calcium-bound forms a little bit than this static image where you see the calcium-free and calcium-bound forms. You do see there's a lot of difference, but it only comes to the full realization when you see the movement, how much movement there is.